Okay, so when is wave-like behavior observed? Yeah, I think so. So when the de Broglie wavelength, okay, lambda is comparable to the dimensions of the physical constraints. Okay, so h has you see that h is a very small number. So in order for you, so when you want to calculate the wavelength, remember lambda is h over p. Okay, since h is a very small number, you would expect lambda to also typically be a small number. Okay, now quantum effects, wave-like behavior will be observed for your particle when this wavelength is comparable to the dimensions of the constraints. So like if you were to pass it through a slit, okay, the what do you call this? The width of the slit must be comparable to lambda for you to be able to see significant interference pattern, wave-like behavior. Right? So Davisson and Germer's experiment in 1927 showed electron diffraction, which is wave-like behavior, from nickel oxide crystals. So what they did is they fired an electron beam on a nickel oxide crystal, and so they have a movable detector here, and based on what they've observed, they were able to show that the electrons do in fact demonstrate diffraction pattern. The wavelength of the electrons used for this experiment is comparable to the typical distances between atoms in a crystal. So atoms are as close as possible in a solid, right? Typically that distance is around 1 to 2 angstroms. So with the electron beam that they used here, having a wavelength of about 1 to 5 angstroms, they were able to see diffraction pattern. Okay, so if you want more information on the Davisson-Germer experiment, you can go to Hyperphysics, the Hyperphysics website. Okay, so if you were to do Hyperphysics, just do a search, Davisson-Germer experiment. Somebody's already done that search apparently. Right there. So this gives you information about that particular experiment. Okay, so that was the experiment that confirmed de Broglie's idea that electrons do behave like waves. Okay, they have a wave-like characteristic. So they have so in other words, that confirms what we would call the wave-particle duality, a dual nature for the electron. Okay.